Ah, le téléphone est où? Ça passe toujours, ça passe. Ouais, là c'est Geo-Distributed qui est encore mis en place. On va pas dire l'enfant.
Yes.
So welcome everybody. So it's my pleasure to chair this committee for the PhD defense of Paulo Souza Jr. So I will present the jury members. So myself, I'm Mrs. Geo-Distributed, director of the research at CNRS, and I will chair this jury. So we have two reviewers, Pierre Souza, who is professor of the university at Sorbonne University, Gail Thomas, the second reviewer, who is professor at Télécom Sud Paris. Then we have two examiners. So François Saillant here, who is professor at IMT Atlantique in Brest. And remotely, we have Federico Facar, who is Chief Technology Officer at Sparkle Lab, so in Italy. And then we have the two PhD advisors. So Daniele Morandi, who is remotely is Chief Executive Officer at UOPA in Italy, and Guillaume Pierre, who is Professor of this university at University of Rennes. So now we have 45 minutes, and then we will have questions.
All right. So thank you very much for introduction. Well, as Anne-Cécile told, I've been under the supervision of Guillaume Pierre and Daniele Morandi, and I'll be presenting my thesis defense, which is named Stateful Application Migration in Geo-Distributed Systems. Okay, I'm going to start with a very well-known thing which is named IoT. It's the Internet of Things, which basically consists of being able to give an address and connecting sensors to the internet, meaning that these sensors are actually able to collect data from the real world and translate it into data. So the big growth of IoT is actually being something which has been a lot in the past few years, as much as many devices are actually being created and being able to produce data. The growth actually of this data has been increasing considerably in the past few years. And whenever we compare with any type of business data, we can see that sensor data has grown like 60 times faster than the traditional like business data. Of course, it actually has been followed as well by the growth of human data, that data that actually people produce from their devices. And this actually reached a scale of like zettabytes already. Many markets actually take advantage of this sector, meaning that many of those markets are actually exploring the Internet of Things by proposing new types of applications, being like the most common ones for like industrial IoT, smart cities, and connected health. Basically, these markets are actually producing applications by using sensor data in order to make decisions and produce output with significant meaning. So how actually can we make this type of process? Basically, data itself by the sensor is not something that you can make a lot, like let's say a decision out of it, but rather something that you need to process or prepare and actually being able to provide an answer or make an action and so on. And there is actually a growth in the past few years, especially for like connected health, entertainment, smart cities, which has showed the necessity of like real-time types of applications, meaning that those applications require, those applications are latency sensitive, meaning that they basically need to be providing fast answers, like whenever the data has been collected, processed, and making the decision out of it. So there is actually a big importance on these types of applications because they need to attend the requirements that are expected in the nowadays activities. So how do we process this data? Well, one of the best candidates for that is something which is very common as well, which is cloud computing. Cloud computing has been is able to provide resources on demand, meaning that your company can actually be able to put your data, process, and put your application at the cloud, process your data, and provide answers to your clients. It has a model which follows like as a pay-as-you-go model, meaning that you can actually hire the resources as much as you need. So basically, there are few advantages on the cloud computing side, meaning that you can actually have a lot of resilience whenever you're using clouds. You can rely upon scalability, meaning that whenever you have an application, you can actually be able to scale your application as you need, meaning that as much as increase the amount of sensor or the amount of clients, you can actually be able to hire resources as you need it. Of course, it has some level of disaster recovery, meaning that in the case like a link failure or any unexpected event, you actually can rely upon the cloud to deliver you another option of link, let's say, or another option of resources that will actually being able to run your application. And of course, being followed by that, basically you have like some high availability that you can actually run your application. It does not fix the entire problem because it does have some limitations, meaning that, for example, you have a lot of limited control in terms of whenever you're running your application, you actually you sometimes it's actually a black box, meaning that you cannot make like very major changes inside the cloud provider service, and actually it limits you on that. It's not very flexible for that reason, and as well it does have like some privacy problems, meaning that sometimes you don't want to place your user data inside the public cloud because it can be actually be reached from different points. It does provide as well in some cases a lot of like high latency, meaning that usually when you rely upon cloud, you have like to choose between a set limited amount of data centers where you actually can run your application, and sometimes they are far from your users and even from your devices that are connected to your application. So how can we actually overcome some of these problems? Well, here's an example like of how the cloud data centers are spread like over the world. This is like from AWS Regional Cloud Network, meaning that you actually have a very limited amount of data centers that you can rely on. For example, like in South America, we do have like one big data center in São Paulo, which is basically everything that you can rely upon. It's not South America, and you need to basically, if you're from another country in South America, you actually end up having to connect to Brazil, which like can be very, very far, and then you actually have a lot of latency because of that reason. And basically, so how can we actually being able to reduce this distance, being able to run an application and attend the requirements of like low latency and basically real timeness of these types of applications? So with fog, actually, we have the alternative of putting an extra layer between what we have as the cloud and also our devices. Basically, you actually can in this middle layer, you can process some data, you can filter some data, you can actually perform a set of tasks of your application in order for you to provide a fast answer to your users, meaning that they're going to be placed very close to your devices and users. So therefore, you actually can being able to reduce the distance. It does not come actually with the idea of basically replacing the cloud, but rather extending all the functionalities that you have in the cloud, meaning that you will keep the advantage of the cloud, but also you're going to have some advantage that actually the fog is going to be able to overcome in the cases of the weakness that we have in the fog. So being like one of these main advantage would be, for example, privacy, meaning that you don't need exactly to move your data to the cloud in order to process it, like specifically sensitive data that from users which you don't want to expose, you can actually process that locally. It does save bandwidth, meaning that you can actually being able to filter most of the data that you're going to be transferred over the network. You can process that in your fog node, and you don't need to make the whole path until the cloud. It does provide a certain level of autonomy, meaning that you can actually rely on the system, like it's a very distributed system. And in the case of failure, like at some point that you cannot reach the cloud, you can actually process and make decisions inside inside the fog computing environment. And of course, it's actually very low latency because you're going to be placing all your resources like very close to your application and to your clients. So, and normally that's the main advantage. Of course, it does come with certain weakness. Like for example, it's actually a very complex system, meaning that you have a very distributed, a lot of resources which are very distributed, and it's very hard for you to manage them, meaning that they have a very high complexity in terms of management. And of course, they are not as powerful as the resources that you have in the cloud, meaning that they usually don't have like as much CPU capability, much memory, and the storage as you would rely upon the cloud. And of course, like as I said, they have like a very limited storage. So what do we actually need to think a little bit? What of kind of applications and how can we actually manage this type of environment? So we think a little bit about like in the way that virtual machines are actually managed and placed inside the cloud and how they actually able to enable the cloud. But in the case of the virtual machines for the fog computing, they actually can be very heavy in a way that they actually take a lot of effort in terms of resources in order for them to run inside this type of system. And sometimes they cannot provide the enough amount of resources in order to run this kind of a virtualization. So, and then we have containers, which is actually a very common thing which is being applied in fog infrastructures. And with containers, you actually can summarize much more as you would have in like in virtual machines. The main reason is basically because you actually can be able to share the host OS inside the container system instead of actually using in the virtual cloud where you can have isolated OS for every virtual machine that you have. So with containers, you can actually being able to have some isolation, share the resources, and you still like have like a lightweight option in order for you to run your application. So how can we actually manage this whole like the mess? Basically, the thing is we have a lot of resources and we have like very limited amount of very limited capability of processing and so on, but it's like highly distributed and you actually can rely upon the quantity instead of like the quality. With container orchestration systems, you can actually being able to manage and reduce the complexity of this type of system, meaning that you can actually abstract part of this management using this kind of container orchestration system. For example, Kubernetes is one which actually has been used in this type of system and actually being proposed as many has been proposed many times in the state of the art for this kind of system and is actually being employed for you to manage like a cloud infrastructure, fog infrastructures. So what exactly happens inside Kubernetes? Well, Kubernetes has a way of abstracting the application, meaning that you can actually place an application as a pod, and this pod it will run one or many containers, meaning that depending that you have like a microservice type of application that you need to basically distribute as much as possible with the abstraction of a pod is actually very possible and very easy for you to do, as you actually can define the amount of resources that you need, the location that you want to place, and so on. You have like a bigger capability of controlling this type of environments. And then you can actually place your volumes as well inside these deployments, meaning that whenever you have a pod, you can put your volumes that you need, and you can actually storage all the data or the persisted data that you have for your application inside that pod. And actually, by doing that, you can actually abstract most of the part of the work, and you just actually tells Kubernetes what exactly type of deployment that you need and where do you want to place it. So we have it. let's assume we have this kind of system and we have our fog infrastructure, which is deployed in the city. Our fog infrastructure has a set of resources which is actually able to provide a certain CPU capability and processing power, meaning. So basically, we can actually place our application inside location A in our cluster, and we know that actually your users are nearby to that location, so we can actually give like a very low latency in order for the users to reach this application inside our fog infrastructure. However, there is the problem that the users may move. So whenever the users start to move, the things start to get a little bit complicated because once again, you start to add an extra hop that you would need to reach that specific application where you first placed in location A. So as actually the users start to move, this distance increase, which actually compromises the whole idea of fog, because what's the difference for you to have like your cloud, which is actually placed very far, when you try to put in the fog and you try to place as close as possible as your first decision, but the users start to move again and you start to get the distance once again. So a very easy way actually to solve this problem, very simple, let's say, not easy, it would be for you to move whatever resources that you have in your location A to your location B. So basically meaning that as fast as we know that users start to move, or you know that something is going to happen from a location to another, we can actually make the action of moving those resources and placing them like once again close to our public, let's say. So actually, this is possible with migration. Migration, it's actually something which is no novelty. It has been applied a lot in virtualized systems and also like in the cloud platforms. Well, it basically consists of moving the application of like between physical nodes. And it's actually, like, as I said, it's very common for cloud infrastructure and it's being used like for consolidation as well. So in order for us to actually overcome this problem of mobility, we need to set up what is exactly what a good type of migration, meaning that we need to do in order to deliver something which is actually going to fix our problem and not generate further problems. So the main idea here is actually to be able to move your application by maintaining and preserving the whole state of your application, meaning that whenever you have your user which is connected to your application, it's using its section and it's doing some kind of task. And we want to actually being able to move your application without your user to realize that its section has migrated from location A to location B. So the idea is actually to being able to recover the service as it was before. Well, another goal is actually being able to reduce as much as possible the downtime. So what is the downtime? The downtime would be basically the time it takes for you it's basically the time that your application is not reachable, meaning that you cannot connect your application and you basically have to wait until it's reestablished. Another goal is like to being able to keep all the network connections open, meaning that basically you cannot just shut down your client. Your client shouldn't be aware that you are actually migrating, so you need to keep the connection open and your data need to be received. And of course, we need to move all the storage that are being actually persisted in that application. So because whenever we move the application itself, actually, we don't fix the whole problem. Actually, if you maintain the data in the same location, once again, we are going to need the set of hops that are necessary for us to actually reach that data. So we need to be concerned about the storage data as well. So we actually wrap up that in two contributions. The first one is actually stateful pod migration. Basically, we conceive a technique of pod migration, which actually migrates application memory between physical nodes in a geo-distributed system. And the second contribution is incremental data volume migration, basically meaning that we can perform data volumes migration in an incremental way without actually stopping the application at the first place. So a little bit of state of the art. Actually, container migration, it's not a very big hot topic. It's actually been explored with a single tool, which I'm going to talk later. But it can actually be divided into main types of migration, which is the stateless type of migration and the stateful type of migration. Stateless type of migration, as its name says, basically consists of not moving the state of the application, but rather only the image that that the application has. So no state is kept. And also it's like a very standard type of migration. It's already applied in Kubernetes, meaning that whenever you need a resource to be relocated between locations, you just tell the scheduler that you need this kind of task and it's going to deliver to you, but it's not going to maintain any type of state. It does perform with like less downtime than whenever you compare to a stateful type of migration, and it can be way less complex because you don't need to care about the state of the application. So in stateful, actually, the main idea here is actually to being able to keep the whole state as it was before. So you can actually be able to restore the container from the snapshot and restore the applications as it was before in the new location. This actually can be classified like in two types of migration, being that live or cold, meaning that whenever you have a live type of migration, you don't need necessarily to stop the application at the first place that you start migrating. Whenever, and on the other hand, you have the code type of migration where you basically have to stop the application and then start the migration process. It does come with a higher complexity because you have a lot of tasks to perform during this migration. You also have to be concerned about the state. And it does sometimes provide an extra downtime because you need to make sure that all the checkpoints are transferred between nodes whenever you restart the application. So this is like an overview about the things that have been used in the state of the art in order for you to accomplish container migration. Being the first line, actually, the ones that have been applied inside Kubernetes, those ones are the ones that are not stateful, meaning that actually you can only perform a type of pre-deployment of your application inside the cluster, meaning that you can actually place the image of your application like in many locations. And whenever you perform this type of migration, you already have a certain part of that image in a new location. And of course, then we have like the other tools, which is actually rely upon the tool which is named Crew. It's a tool which was created for us to actually being able to migrate containers. It's a checkpoint restore in the username in the user space. Basically, here this tool it's already applied for Docker, for LXC, and so on. And it's actually a stateful type of migration. It does create a snapshot of that container, and you actually can recover the state as it was before. However, it's actually a little bit, let's say, it's an application which takes a little bit of time for you in order for you to create like a checkpoint. It's actually wrap up the entire container, brings all the files and everything that you need for you to start up your application. And then we have some enhanced versions of Crew, which basically try to overcoming this weakness of actually having to wrap up everything and being like very heavy in a way that actually takes a longer time for you to create this checkpoint. The work of Fernandez actually tries to run most of this process into memory, meaning that whenever you run this into the RAM, actually you can perform a little bit faster than actually persisting that into the disk. And then there is our proposal where we try to deliver like something which is stateful. It's actually performed lively because you can actually run some tasks of the migration before actually stopping the application. We do create a pre-copy, meaning that you can actually place the image even before the migration starts. We do create a snapshot of the running process inside the pod, meaning that actually whenever you have a pod, you may have many containers, so you can actually are able to create many checkpoints for every process that you have running inside your application. And of course, I think one of the most important is actually being able to provide a transparent solution, which actually kind of abstracts the migration, and the user itself don't realize the migration is happening, and not even the application itself realize that is being migrated, meaning that you can wrap up your process, take the snapshot of that process and reestablish as it was before with its sockets and its memory as it was previously. So a little bit about data migration in general. Like whenever we think about data migration, this is like no big novelty as well, meaning that whenever you have like your data inside the cloud, you can actually easily just reattach your volume, like from VM to VM or from container to container. There are some alternatives that have been discussed for like fog environments. It's actually being able to just replicate and sharing volumes, meaning that all the modifications that you actually perform in your volume actually are going to be replicated to your volumes, which are like distributed into your infrastructure. This is not the best of the ideas, meaning that basically you can overflow a lot the bandwidth by doing that, and it can be very heavy for the system to handle that. So as I said, like normally you would rely just on reattaching the volume after the migration. And this is not feasible for us because whenever we do migration between locations, if you don't move the data, if you just reattach the data to the volume to the pod, actually there's still the path that are going to be done in order for us to reach the volume as it was there before. So there is like a small overview here about the things that have been proposed in the state of the art for us in order to perform data migration. Most of them actually, well, this one actually consists of stopping and migrating and starting again. And most of them actually use some kind of sharing file system, networking file system, or try to replicate or the file system over the environment. And then we have our contribution where we can actually perform stateful type of migration lively. We can create an incremental types of checkpoints that are actually able to be transferred before the application is stopped. And we do care about network bandwidth, meaning that you can actually avoid like big transfers, but rather transfer it as it's necessary. So contribution one is basically it's the stateful memory migration. We actually propose here a tool which is called MyStrive. It's basically a technique for us in order to migrate containers by using DMTCP. Well, its main goals consist of being able to capture everything that's running inside the pod and place it as we wish in the new location and run it from there. It actually has the other goal is basically being able to be transparently to the application, also to the users, meaning that users do not realize the migration, and also the application can be unaware of this, and that's actually happening. It does have like certain generic support as much applications as possible, meaning that we can make it a little bit generic and can be applied to many deployments and type of applications, and actually being able to reduce the downtime whenever you compare to the rest of the solutions. So just explain a little bit what is DMTCP. Well, DMTCP is a distributed multi-thread checkpointing. Basically, it consists of like creating checkpoints out of processes. It's used for like process migration and is also used for like process replication. In general, like there is no need for you to recompile your application or make like any changes to your application whenever you want to use that. It's rather something which is generic and can be applied as much as possible of types of application. It's actually one of the goals of DMTCP because they say that if they have some problem on checkpointing your application, basically it's their fault, like the DMTCP fault, because the goal is actually to being able to support as much application as possible. So basically they try to fix as soon as you realize this type of bug. So DMTCP in general, it does not require any root permissions. You don't need to make bigger and major changes into your kernel. It's rather something which is supposed to be simple, and it's supposed to be easy for you to implement in your environment. And of course, it does supporting as the usage of plugins, meaning that you can customize it depending on the type of application that you have, like specifically like for third-party add-ons. So just explaining a little bit of the system architecture of MyStrive. It's actually constituted by three main components, which like the migration coordinator, the DMTCP container, and the execution agent. So each of these components has a specific task, meaning that the DMTCP container is basically concerned about providing all the binaries necessary for us to actually being able to wrap up wrap up the application. And actually, it's actually whenever it starts up, it provides like those binary files of a persistent disk, and it's actually shared with every container inside the pod. So actually, the execution agent, whenever the pod starts or ends, it actually can use these binaries in order to wrap up the process, create a checkpoint, and finish the application. And we have the migration coordinator, which is actually the one responsible of like interfacing with the Kubernetes API, meaning that whenever you decided that you want to migrate resource your application from one location to another, you're going to tell migration coordinator to do that, and this is going to be translated into the necessary tasks that need to be run inside the Kubernetes API. So whenever we need to run migration, migration coordinator is going to be responsible of like creating and deleting the pod as we need it. We actually use a labeling system inside Kubernetes in order to be able to identify specifically what pod we need to migrate, and also to place the pod where we need to be placed. Basically, whenever migration happening, there is actually a sign of deletion to that pod. And whenever a sign of deletion is received by the execution agent, it's actually able to see, okay, I have this running process, like which were being wrapped by the MTCP files, and I need to create a checkpoint out of them. So actually, whenever it creates the checkpoints, it lets the migration coordinator know that the checkpoints are created, and then the files are able to be being copied to the new pod location. So it's actually execution agent makes sure that all the processes are actually properly checkpointed, and the application is actually able to be restarted in the new location. So once that actually receives in the new location, the execution agent once again is going to receive the checkpoint and is going to restart the application. There is during this process there is a small interval where it is actually necessary for us to create a temporary route, meaning that all the messages that are being received for our service, like all the requests, are actually sent to our pod. And whenever this pod is ending, we need to create a temporary route for us to being able to receive the message and not lose any type of message between the pods. So this temporary route is actually just during this interval, it's used, and later on it's like discarded. Basically, whenever migration is concluded and the checkpoints are actually fully restored, we actually update the Kubernetes service, and we tell that your new pod is actually placed in the new location, and all the requests that are being received to that pod should be routed to that specific location. So that would be the end of the migration. So in order to evaluate that, basically we did evaluate over 3 different techniques, being the MyStrive, the one that we proposed. We did compare with Crew, which is the most popular tool for container migration. And we did compare as well with the regular Kubernetes deployment, meaning that basically you have no state whatsoever, and you basically delete and create a new pod from a new location. We did evaluate like under low bandwidth, meaning that sometimes in this kind of system, you cannot rely on a very powerful, like on a very large type of bandwidth. And also we evaluate like over 3 different applications which are very common for microservices. So this is first results actually shows the migration duration. This is the time for us that it takes to make the migration. We actually want to make sure that the Kubernetes migration is stateless. This needs to be clear, like because we are comparing stateful, and stateless type of migration here. The idea is actually just to show the time it takes for us to do a regular stateless migration, and show that with the stateful type of migration, you can actually reach kind of the same duration. So we can see here that basically MyStrive can perform migration like way faster than the Crew type of migration. It actually repeats itself in the same as for the other applications as well. But I think the most important here is actually the downtime. Basically, it's the time that it takes for us to reach the application. We can see that whenever you use MyStrive here, we are actually have like up to 6 times less downtime whenever we compare with Crew. Like Crew takes a long time for us to perform migration because there is a lot of procedures that were run in the meantime. And meanwhile, with MyStrive, we can actually parallelize most of those tasks. And also we can actually compare with the stateless type of migration, which is basically the one that we are actually just deleting and creating a new pod. The same thing actually happens during migration, but the thing is here is that we can actually parallelize and start some of these tasks earlier. So meaning that we can actually reduce the downtime further to close to zero. We can see the same behavior as for the other applications, like instead of like the Redis here, because it actually was really faster whenever you compare with MyStrive. But I think the main point here is actually that at some point, what actually takes time is the data transferring. Like the data transferring is the one that actually defines pretty much how much is going to be the downtime. So about the second contribution, which is incremental volume migration. Well, its main goal is actually being able to move your data and place it as close as possible to your application. The second goal would be for us to reduce the intrusiveness of that tool, meaning that we don't want to stop the execution whenever you create a checkpoint, and being able to not interfere with the application. And we also want to guarantee the downtime and the data consistency, meaning that we cannot compromise the data of the running application. So we propose a technique to incrementally migrate volumes data without interfering with application runtime. Well, in order to achieve this, we used like an overlay file system. We built that overlay file system, and basically with overlay file system, you can rely upon multiple different underlying mounting points into a single one, meaning that actually all the lower layers are normally read-only type of layers and no modification is made on them. And you usually, whenever you perform some type of modification or like this task, you can actually do in a single and and separated layer. So by doing that, we can actually isolate the files between the layers, and we actually are able to create a checkpoint from the moment that the migration starts, and we can move both of the things that have been changed earlier to the new location and without compromising the execution of the application. Whenever we create a new checkpoint, it's going to just withhold the difference and the delta from the point that we created the checkpoint. So once that we actually conclude the data transferring, we are able to move this checkpoint which is placed in a higher point of the overlay file system to the new location, which actually tends to be smaller because it's just the delta of that volume. So in order to evaluate this, we actually exercise like a RabbitMQ application, which is actually persisting MQTT broker, meaning that we actually run a perf test, which is actually producing data and is persisting data into the disk. We do evaluate like over different numbers of checkpoints, meaning that, for example, for 0 checkpoints, we do not create anything. It's rather just stopping the application and moving the data from location A to location B. Once again, we evaluate like over smaller bandwidths, like in order to being able to see of like the impact of the technique. And we did apply a pre-pull type of strategy, meaning that you can actually recover and move the image of the container beforehand, actually the migration. So what we actually can get on that. So here's the average message throughput whenever we run the migration. In this case, like we are actually have 0 checkpoints, so we need to stop the application from the point that we actually start the migration, and we need to move in the meantime all this data. And once that's actually moved and loaded into the file system, once again the migration ends. Here we actually have like one checkpoint. At this point, we don't have to exactly stop the application at first glance, but rather actually perform the copies and move the whole volume before actually stopping the application. And this last checkpoint is just transferred afterwards and loaded into memory as it's actually arrives. And then we have like the one with 2 checkpoints, meaning that we can actually perform more tasks. We can actually create one more checkpoint before actually stopping the application. So you can actually, I think it's going to be more clear now, we can reduce further the downtime, meaning that whenever we compare to not using any type of checkpoints, we can actually reduce it like up to 4 times of the downtime. There are some cases whenever we apply the pre-pool, like when we have like a better bandwidth, we can actually get even more like and reduce the downtime. So it's actually something which it would be ideal for us to run in our system. So as I said, it actually can reduce the downtime like by a factor of 4 whenever you compare 0 to 2 checkpoints. So as conclusion, well, there is requirements that are like showing nowadays of latency sensitive type of applications, and those requirements are actually increasing as actually this pretty much defines the quality of the application, meaning that nobody wants to use an application which takes time for us to load something, and this is actually needs some kind of attention. And fog computing comes as an opportunity to reduce this long distance communications, actually overcome most of the like weakness of the cloud. However, it does not fix the whole problem, meaning that we need to adapt our system to being able to adapt to this to the mobility of people, because people move, people are expected to do different things, and we need to be prepared in order to adapt our system to this kind of behavior. So in general, we propose like a migration techniques which grant an opportunity to overcome all the mobility issues that we found nowadays. So our contributions were basically the stateful pod memory migration, meaning that we can actually migrate pods in a stateful way and place it in a new location as it was before. And also the second contribution would be the incremental data volume migration, meaning that we can actually migrate our data over like a distributed file system, distributed system, sorry. As final remarks, we actually, the contributions of this thesis basically grant a full migration approach, meaning that you can actually achieve like a good migration for your system, and you can actually extend the containerized system functionalities in order to overcome the nowadays challenges. As publications, I did 2 publications, being the first one about memory migration, and the second one, being the first one about volume migration, and the second one about memory migration. I do have like some future directions, meaning that actually there is an opportunity for us to improve the memory migration, meaning that we can actually extend the functionality of DMTCP by using the hash-based incremental checkpoint tool, which is a plugin for DMTCP. So we can actually perform an incremental memory migration, which is very similar to the one that we did perform for volume migration. And the second one would be integrating both of solutions and providing a component for Kubernetes, which is actually able to grant a full migration technique and is actually tries to reduce as much as possible the complexity of this deployment and being able to your system to self-adapt as well. And that would be all. Thank you. Questions, I suppose?
Thank you. So we'll start with the question of the first reviewer.
Thank you. Thank you, Professor. Thank you for your presentation. I enjoy your presentation, and the quality of your presentation reflects the quality of your manuscripts. Congratulations for that. As I wrote in my report, you address an important issue for computing, and I have particularly appreciate your experimental part of your work with elimination of thought. So sure, I have some questions.
Yes.
First, in my approach, your migration controller is centralized.
Yes.
So I think the placement of this controller is a key point. When you move, do you have some suggestion where to place the controller or to extend your work, considering the distributed controllers or something like that?
Yes, we actually consider to be like a distributed controller, meaning that you actually turn this into a daemon set inside Kubernetes. So basically, we can actually place as many of them as we need in the way that we can actually make sure that we can scale like many migrations happening at a time. Because in any ways, actually, they need to communicate with the migration coordinator. This is basically an API which is responsible to make sure that the whole process is actually synchronized. So we could actually place it as a daemon set, which is actually placed in many locations to make sure that in case of any failure, like we can rely upon another one.
But in your evaluation, in any case, you have only one controller.
Yes, in this case,
You
just
don't
one
make any
controller.
evaluation with several controllers.
No.
And also in your evaluation, you consider relatively simple applications. For instance, if your application has many controller, many containers distributed in several pods, to move to checkpoint this kind of application, I think it's not so easy for to maintain the consistency of your checkpoints.
Yeah.
Because using the MTCP, you only ensure the consistency inside one pod. But
Yeah.
if your application is distributed on several pods, how you ensure the consistency of your checkpoint?
All right. So basically, the MTCP, it's a distributed multi-thread checkpoint restore tool, and it's actually able to checkpoint many processes at the same time, meaning that actually you have like a DMTCP master where all your processes are going to be connecting. So whenever you need to create checkpoint from a specific process, you tell the MTCP and it's actually going to handle all the connections and all the processes that are connected to that process to make sure that it does have like a consistent state.
And the DMTCP froze all the application because you can have message in transit.
Yeah.
For the consistency, so you flush your communication channel, or I don't know.
Well, in this case, basically, there is a period, which is a gap where everything is frozen, meaning that everything, not really everything, sorry, just the part that you need to migrate. So whenever the rest of the applications want to communicate with that specific application, they're going to wait because it's actually not available, but they are aware that actually they are connected, meaning that you can actually, it identifies all the sockets that are connecting to that application. So you, whenever you perform migration, you're actually able to restore as it was before and connect back again to that socket. Because the whole idea here is actually to be able to checkpoint like distributed type of applications. And yes, in my evaluation,
yes, but just to come back to my question, because here it's okay for the consistency, but if all your containers are in the same pods, but if you because you have one DMTCP master for each pod.
That would be yeah.
Yes,
exactly.
but if your application is in several pods, so you have different master, and this master, the MTCP master, need to synchronize to have a consistency.
Well, in this case, they don't,
okay.
but rather they would.
It was my question. If your containers, your application is distributed in several pods, maybe it makes no sense.
Yeah, it makes totally sense. Meaning, of course.
My question is how you ensure the consistency of migration in this case, if you have several pods and several DMTCP master.
Mm-hmm. So in this case, actually, whenever you have like a distributed between pods type of application, you can. I don't see the consistency problem, meaning that you know
message in transit between the containers of different pods.
Yes, but they communicate over sockets. So actually, well,
I'm not sure.
Well, depends on application, one would say, but let's assume that they communicate over sockets. In this case, yes, we could make sure that actually the consistency is kept. And that's precisely the scope was like, we go toward like being able to keep the connections open in terms of sockets. So like whenever we need to do this more complex type of migration, we can actually keep track of those sockets and then deliver with something which you can rely that's going to be consistent.
So you have to implement some kind of distributed checkpoint, consistent distributed checkpointing between the pods.
Yes.
Implement some kind.
Yes. Or you could use like a different approach. For example, you could bufferize the incoming message in the meantime. Could be a way.
Yes,
we actually thought about that. Maybe we could have like a mock service that would make sure that all the message were going to be received and delivered. But in this case, it was not necessary.
Maybe another question concerning the migration of volumes. In fact, I don't understand your protocol when you have several checkpoints, 2 checkpoints. Can you give more details? When you take your first checkpoint, when you take exactly your second checkpoint, your protocol, which is not so clear.
Okay.
You don't give the algorithm. So.
Okay. So whenever you start the process of migration, you create your first checkpoint, meaning that everything that you have like at your higher layer are pushed down. So in this point, you like, for example, in the experiment of one checkpoint, you just create an one extra layer. And once that all the data that which is actually placed down in the lower layers actually are moved, once that they're finished moving, the application is stopped, and only the remaining delta from that layer is moved. So in the case of two, like you would have like one extra layer. Like once that it's actually finished, you create another layer. Everything that was in that delta is pushed down, and then it's moved. And once that it's moved, actually the application is stopped, and the remaining is moved. Yeah, because that's exactly why whenever you increase the amount of checkpoints, you actually don't get some gain, meaning that actually at some point the checkpoints are so small that there is no reason for you to go further. You know?
Yes, no, yes.
Yeah.
It's not clear. Another question. Yes, you mentioned an interesting future work to use incremental DMTCP.
Yes.
So your objective to decrease the migration downtime. If you use incremental DMCP, you have so you make sense only if you migrate in the same location, or because if you migrate to different locations, you don't see how you're using incremental DMCP can improve. I don't have the heading you are using incremental DMCP. The same technique you apply for volume migration, you start. For me, it's not clear.
Sorry, I didn't.
My question is, but what do you have in mind?
I will try to paraphrase.
Yes.
Basically, here, so why would we use like incremental DMTCP type of migration? I think the first goal here would be for us to being able to reduce the downtime, meaning that we can actually proceed transferring memory state even before the migration actually occurs. So we can actually do something which was similar to volume migration and try to reduce as much as possible.
That it means that you know in advance where you're going to move.
Yes.
It's realistic.
I think this goes towards a little bit out of the scopus, like meaning that we wanted to deliver a technique which is generic and you can actually place in your system and rely upon like whenever you need to do a migration, like you decided to do a migration. There are many things that would make you to do a migration, and the idea is actually to provide the opportunity to these people to being able to do this migration in the most effective way as possible. We know that, for example, downtime is actually something which we cannot avoid, meaning that you cannot reestablish the application as it was before without stopping it. That's like very, very complicated, meaning that you would need to do something which is buffering the requests or so on. So the idea here would be for us to try to reduce the downtime, assuming that we know where we're going to place our application. So like we know where we're going to do our application, place our application, we can actually perform this migration incrementally, move our data, and start the application back again.
Okay. Just maybe a small question. In your slide 30, when you see that your approach, you have a higher standard deviation using a nice drive compared to CL.
Yeah, in general, Redis has behaved that way, like even for downtime. But it's actually something which has been shown to be constant, like even for downtime. To be honest, I think this is something about Redis and how actually the application is started up and actually being able to restore the socket, meaning that the MTCP delivers like something which actually try to establish the socket. But even though I think the application itself has some time like interval inside of that in order for it to reestablish its execution. Yeah.
Just okay. Yeah. So thank you. Thank you for.
Thank you.
Thank you.
Thank you. So we will now let the second reviewer first question. Gael.
Okay, thank you. Thank you for your presentation, which was very clear, just like the document. So it's a pleasure. So it's a very interesting work. For computing is something that should occur. On, I imagine, I hope. And migrating containers in this case is a very interesting subject. Of course, I have some questions. The first one is just for the setting, because I'm not an expert in fog computing. So I don't know, what do you imagine when you say the user move? What is the scale? Of course, if I'm going to work at 30 kilometers, is it far or not? Or is it for holidays? What is the idea?
I think this is very broad, meaning that you have situations where you don't have like significant mobility, but at the same time you have situations where you may have like a lot of mobility. Meaning, for example, I can give you an example of a rock show, for example, which is placed in a city. And for some reason, we decided that all that people is going to gather there. So why don't you actually use to place applications that would normally be placed in a location where you have like condensed amount of people, like a lot of people, also to that location. So whenever these people are actually using their phones, using their application, they're actually able to actually have a fast answer, because we know that whenever you go to a show or to a place where there's actually a lot of people, connection is actually not good in general, and you're competing with many people. So why don't you actually place all the resources there? So we actually are able to, besides of providing much more like bandwidth, but also like providing that the application is going to be there and is going to provide fast answers, like trying to reduce as much as possible the communication, you know. There are many cases. That's why I say that it's actually very broadened. Like we could assume that people move for many and different reasons, which is actually really, really hard to map. So the thing would be a question more about towards like, when do you need migration? And this is not exactly our goal here. It's rather to provide something which can actually facilitate this type of system and enable this type of system to actually move your application and provide as much possible quality of the service that your infrastructure can provide. You know, I'm not sure if I answered your question.
The idea of allocating resources, because many people arrive at the same place, really makes sense for me. Because I have a nice example with one of the first Pokemon fests that took place at Chicago, and the server were
I
down.
know.
It was incredible. So
yes.
You propose a perfect solution to save the Pokemon players.
Yes.
It's very important.
Yes. Very important. I mean, I'm a player.
So your idea that you migrate between one edge data center to another one, does it make sense to imagine migrating a container from an edge data center to a main data center, a cloud, on the fly, because of consolidation, resource allocation? I don't know. You can imagine that you don't have enough resources locally. And does it make sense? And does it change something for your prototypes or not?
So no, that wouldn't change, because we actually assume that it's actually connected to the cloud. So we don't see why wouldn't be able to move wherever you have running in a specific edge node, fog node to a cloud. there would be no thing that would say otherwise. The only problem could be regarding architecture. We do providing a certain level of like compatibility because the MTCP is able to run multi-architecture, even though it's actually something that has been worked on, and it's like, to be honest, it doesn't work quite well. And if you have like different architectures, it might be a problem. But it actually depends upon the type of your system specifications rather than that. But yeah, you could totally move wherever you have in your fog to your cloud and vice versa. So you can actually make this decision whenever you seems that, for example, your cloud is being too expensive. Maybe it's like cheaper for you to place your application in the fog, even though it does not provide like a powerful CPU power, but you can actually place and save some money because it's the moment of the day that you're actually not have many users using it. So there are like a very big range of like situations that you would use this approach.
I have a question related to what Pierre asked a few minutes ago. It's related to the problem of data of interdependencies between the containers inside a pod. So let's imagine you have a WordPress and you have a MariaDB. And you migrate the two containers. At some point, if you restart the WordPress without the MariaDB, it will not work. So how can you handle this kind of problem when you have internal dependencies between the containers when you restart them?
That's a good question. This is actually something which was actually leaving to the coordinator, because like whenever we are performing the migration, the coordinator is responsible to decide like, okay, you can start. Basically, you have your checkpoint, you can start. And I didn't put any lock on that, meaning that whenever you receive your checkpoint, you can restart your application. And of course, if you don't have all the remaining containers that are part of that application, they would have to wait. There is no other thing that we would be able to do, meaning that like you can of course parallelize this process of moving the checkpoints, like you don't have to do like one at a time, but if you receive something first, you have to wait for the rest. This is something that there is not much that can do, like, because in general, like the solution itself is supposed to be generic, like it should be able to be applied as much application as possible, but we do know that there are specific situations where there will be dependencies between both of them. So there is nothing the two can do, but rather like to wait.
The problem is complex because
yes, it is.
Dependency at deployment time does not mean that I have the same dependency during at runtime. Because I can imagine you have to start your MariaDB, then your WordPress, and at some point, I don't know why, MariaDB want to reconnect to WordPress later.
Yeah.
So for the dependency problem, it's very complex. Okay.
Yes, this is something which, to be honest, I didn't handle. It was most like leaving to the coordinator to recover as they arrive. I can think of a situation.
You cannot simply just try to synchronize all the containers when they restart and try to restart them almost at the same time, and after you pray because you have TCP reset and stuff like that.
Yeah, but this is kind of what already happens, meaning that once that all the checkpoints are received, the application is started. Like it makes sure that everything's there because they are waiting. This is something which is very similar to what happens to volume checkpointing, because with volume we cannot start the application. So we need to wait that all the things are there and the file system is mounted, so actually that you can start your application, because we don't want to have problem with consistency.
I have another question regarding the configuration where you have multiple containers inside the pod. I don't see if you migrate the container in parallel or if you accumulate time for the post time and or the downtime, the full migration time. If all the migrations are executed in parallel or sequentially when you have multiple containers?
They are executed in parallel, meaning that they have like every one has its execution agent. So whenever every running container has its execution agent, and this is the one that's actually supposed to wrap up the process. So whenever it actually receives a sign of sigterm, basically that the container is dying, it actually makes sure that the process which is actually wrapped creates a checkpoint and moves that checkpoint before actually ending. So this process is triggered to every execution agent which is inside the pod, and they are going to happen at the same time.
So you are only limited by the bandwidth between the
exactly. Yes, at certain point, yes.
And another question, you try to. We have a solution when we migrate virtual machines to minimize the downtime. It's to use what we call CPU throttling. So we reduce the frequency of the CPU, which means that the workload decrease and the number of dirty pages, dirty sectors on drives is lower.
Okay.
Did you try that or not at all?
No, not at all. No. But it's interesting because you actually have control like over the processing power of a container. So you could do something similar. But I think that would be very intrusive to the application.
It is.
Yeah.
We have some measurements that should say it's very intrusive.
Yeah.
Another point around the downtime. On the next slide, the downtime is around 10 seconds, as far as I can see.
Yes.
10 seconds seems huge. Do you know why you have such a large time?
Yes. In general, it's actually about the bandwidth, because you don't have like enough bandwidth to transfer your checkpoints. So the checkpoints actually take some time for you to move this, because whenever you have like the whole process, like the whole procedure inside Kubernetes about the scheduler to make the decision to create that pod and to delete another pod, this takes time. But this actually can be you can actually hurry that process, and we managed to do that. The thing is, like the time that actually the application takes for us to create a checkpoint and to move the checkpoint is usually what defines the downtime. And also, I'm sorry.
Okay, you don't have pre-copy cycles, just like
no, I mean
the drive. Okay.
No. This would be like the pre-cop cycle would be something which happens in an incremental way for the volume. But in the case of the memory migration, the pre-cop cycle would be moving the image before, because what we take it's only memory, So we need to have like exactly the same image as we had before. And since the image does not change, like only the thing that would change would be the higher layer.
Yeah.
So
I was thinking that you are using, not you, DMTCP was using a technique that we use when we migrate virtual machines, where you let the virtual machine runs on the source node, and you migrate the memory, and then you migrate all the dirty pages.
No, that would be something.
Okay, it explains why your performance are.
Yes, but that would be to the direction of the incremental DMTCP migration. In this case, we could actually isolate the dirt pages and move it afterwards.
And in your setting, so you have a downtime of 10 seconds. I imagine that you have a load injector for MongoDB, Redis.
Yes.
I don't remember which injectors you use.
Well, I do have like some applications which are actually producing and stashing some data. For example, for Mongo, it's actually adding data into Mongo. The other one is basically producing data to a Mosquito queue. And the Red is also injecting some data. Okay. But I don't have like a specific injector. I'm implementing my own application in order to use it.
Reusing YCSB? You can connect YCSB to MongoDB and
yes.
It's easier.
Yes, that could be. Yeah.
And because 10 seconds of downtime is huge, and I don't know if your TCP connection resists during 10 seconds if they don't have acknowledgement.
Yes. Well, actually, with the TCP, it was possible to actually manage for those 10 seconds. But actually, it's actually like able to isolate the system call and actually being able to guarantee that it's going to keep trying, you know. But yeah, you're correct. That was something that was needed to be tuned inside the MTCP. But in this case, since we didn't have like a lot of bandwidth, we didn't escape of that time.
Yeah,
you know?
sure.
So there is like rather something which was like a workaround inside the MTCP, but rather than actually losing the connection. But we can see this to be improved. Like whenever you have like a better bandwidth, you can actually reduce your downtime like very close to zero.
And you cannot imagine running a module inside the kernel or something like that, able to acknowledge the message during the migration to just simulate a live node or something like that.
Yeah, yeah. That's what goes a little bit in the direction of like having the SMOG service, which makes sure that the data is being received and actually being able to also forward the data whenever it's actually finished, the migration is finished. But this is something that we didn't do. That could be a way.
No,
yes.
Okay, this is 3 years long. You can do.
Yeah, yeah.
Okay, thank you. That's all.
Thank you.
Thank you. So now we will start with the examiners' questions on the first ones.
Thank you for your presentation. I would say that the presentation were very clear, and you present well your two main contributions. The same applies with your thesis. I have one question. I think it's around the slide number 39. Or maybe, yeah, no, before, sorry. Yeah, I think that it is. Yeah. Okay, I see that the you have a downtime that is reduced with the first checkpointing and the second one. The question I have is why you have the start of the you start the migration and its end. And the question I have, it seems to be reduced. The time for migration seems to be reduced with checkpoint 1 comparing to checkpoint 0. Perhaps I'm false.
So you basically want to know like what's the main difference between the checkpoint 0 with the checkpoint 1?
It's checkpoint 0. I see, for example, I don't know, it takes 2 seconds to migrate really.
Yeah.
Let's suppose that checkpoint 1 it's a little bit reduced, and checkpoint 2 it's increased again. I don't know.
Well, this is actually, it has a lower downtime whenever you compare with checkpoint 1. You can actually reduce a little bit the checkpoint here, even though it's not that significant.
Yes.
You can barely notice here. Actually, it's more noticeable here.
It's more the time for migration, the overall time of migration. Is that increased for?
You mean the start and the end of the migration?
Yes.
Okay. Well, yes.
Why?
Yes. So in general, like what I did here was I was trying to be fair, like with the things that I was comparing. And here you actually stop the application, start the migration, and once that you send the files, you basically end the migration and you restart it. This spike is basically the time that it actually takes to load everything like back again into the application. Here you have a smaller migration duration, basically because you just have like one checkpoint. So usually it's actually faster for you to recover all the things into the memory. Okay. But meanwhile here, you actually have a set of tasks that actually you want to make sure that data has been recovered. So this is actually 2 times more than here. So you actually have a moment here which actually takes a little bit longer for you to make sure that the volume is actually loading and everything was loaded into memory.
Okay.
So this is like more like a synchronization result of the migration rather than something that has actually impacted the application itself. Yeah.
I have another question. In fact, you are interested in IoT, and which is kind of application. of interest for you. Is there any specificities of the IoT? Is there any specificities with regard to migration? I mean, is there specific properties of IoT application comparing to, I don't know, whatever a cloud application exists? In fact, did you see some difference and, I don't know, some trainings that are necessary or some?
Okay, so not really. I didn't check like in specific, like very specific things for every type of these applications. It was rather something which was supposed to be more generic that could be applied to IoT as well. I know that like IoT have like specific requirements, and we actually, the things that we try to pinpoint here, it's the, for example, the connected health type of applications, like health applications. They do require like low latency and also like they are latency sensitive types of application. And this is actually something which actually motivates the work because, I mean, we don't want to compromise an entire application, but rather actually being able to reduce the latency by using migration inference in order to improve the quality of that application. But I didn't look specifically like between the differences of these types of applications.
And when you are looking at MQTT, for example, I don't know, there is manager and manager and so on. I don't know, is there a structure of container you could?
No, it's not a very complex structure. It's very simple. I mean, we wanted to be simple in our results, being able to show that we actually can provide a migration technique which actually can reduce the state of the art whenever you compare with the ones that already exist, like to the state of the art. So it's very simple. It does have like a queue, and that will be all. I didn't go towards that direction. Sorry.
No. Just the patients criticize also. Okay,
all right, thank you.
Thank you. So we let the plans to the second examiner with Federico. Yes.
Should I?
I think you called my name. Is that correct? Sorry, but except Paulo, the others look very far away for me, so I'm not always having a clear understanding. Okay, so
well, I can. Well, I wasn't going to talk now, so I'm going to keep like here.
Yeah.
Can you see?
No. Yeah. I can see you. It's fine. No. I was just unsure that I've been called to express my statements, and but yeah, I guess so. Okay. So first of all, thank you very much, Paulo, for this interesting work. I found a very interesting concept inside your thesis. But I also it raised me some thoughts, and I'm. It's a bit of time. I don't know if Daniele mentioned that I'm not doing the research. I'm more now working in the industry side, and my first question here is, while you can see really that on the virtual machine type of workload, this was and is a very hot topic. And in fact, for example, you see that there are commercial solutions running in production for doing different type of migration modes. And for example, there are inside vCloud, VMware, and so on. This is not yet the case for container orchestration. And so my first question is, what is your take on why this is not yet becoming a hot topic in commercial or open source production-ready solutions? If this is related to a problem of maturity, or simply it's quite a different the condition and that you have between virtual machine and containers, and maybe then in the case of containers is so not much needed as in the case of virtual machines.
I think it is, yes, somehow a little bit of a problem regarding maturity. I think this is something that's actually walking to that direction. I mean, everything is quite founded upon virtual machines, and this is quite common that it's been the one that has been explored for that sense. And containers somehow it's something which is quite well, maybe it's not really new, but something which is like starting to move and starting to being like adopted by different for different areas. And I think it's something which actually creates a lot of opportunities for us to provide solutions and try to actually mitigate further and improve this kind of system. Also to give it like more maturity in a way that actually can be explored in the future, in a way that whenever we think about the fog environment, that could work up well, and could benefit specifically this type of environment, especially if it's actually started being adopted by big companies. We actually can see that Google have like many points of presence, what they call, which basically a small cluster which they place like closer to somehow to their data centers, but still they try to be a little bit far and being able to deliver some of the resources in those places. And I think this kind of environment at some point is going to use like more lightweight options of virtualization, maybe. And I'm not sure if I could say that, but basically, I think this is going to walk to that direction, and I think providing solution to specific this kind of type of system is something which is quite necessary. And yeah, that would be pretty much it.
Yeah, but I mean, I think and I'm thinking to my practical experience, let's say, because we use in our production environment Kubernetes. And of course, we have also stateful set, and this means we have distributed infrastructure, and this actually means that sometimes we do migrate workloads, and I think there is somehow a point which is not surfacing neither in the discussion, neither much in the text, which is how today is practically tackled the type of issue that you have, and in my experience, the truth is that most of and this might have its own advantage and disadvantage. So it doesn't invalidate the work you have done, but not taking it into consideration, I think it becomes a bit a weakness. The truth is that in most of the cases, these stateful workloads, like, I don't know, MongoDB is one you mentioned, Redis as well, for sure other, I'm not sure about RabbitMQTT because I have not been using it, but MQMX or another type of broker, all have some solution themselves, which basically means that when you deploy a stateful set, which is multi-instance, they have inside a mechanism for synchronization. This also implies that when you kill an instance on affinity, anti-affinity, and other type of annotation over the stateful set, what is happening is that the Kubernetes by itself is ignoring, it doesn't care about managing the state, because in the end, what is happening is that the state is managed by the application itself. And in relation to this, I believe that a comparison because to me this is the state of the art, because this is somehow how you do this migration today in Kubernetes. And again, I'm not saying that it's better or you can achieve better numbers of what you showed up today, but what I want to say is that today you are not, in my understanding, showing a comparison with this case, which I actually tend to think that might even come up with stating that a real migration in Kubernetes compared to what you call their stateless migration is much worse than that numbers. But it's a kind of rough estimation based on my experience. But so this was for me something that would have been interesting to show in the experiment, because this is in the today real cases how you do this type of migration in Kubernetes. So I don't know if you want to comment on this, then I have other things, but I want to put everything on the table.
No, I can comment on that. Actually, yes, indeed, like you have like many tools that actually provide to you a certain point of being able to checkpointing and actually moving those checkpointings from location A to location B as much as you wanted. Like, and this is something that's actually being delivered by many tools. Like there are even like big data tools that for streaming that actually allow you to do that. But the things here was basically that we wanted to be able to enable this type of system. So why those orchestrators, like container orchestrator, are not being able to provide something which is inside, let's say, its core to us to being able to migrate applications. This is something which is actually being very interesting, meaning that not all the applications actually provide this type of options. So there's actually an opportunity for us to provide like a generic tool that can be put inside your orchestration system, and that you can actually perform migration there. I know that those tools provide somehow those kind of solutions, but they're very specific, and they usually actually restrict you to that specific type of environment. So let's assume that you would want to have like a different deployment where you basically cannot rely on all of those tools. So you actually start to getting limited. And the whole idea here is actually to being able to extend your possibilities inside your system, meaning that you can actually tune a little bit in your infrastructure and actually perform and provide a migration option for your system. That would be my commentary. I'm not sure if it makes any sense, but
yeah, I think it makes sense. Still, I think that would have been very interesting, given that you picked Redis and Mongo that provide this mechanism themselves to have a comparison of with the mechanism they provide also, I wanted to raise another question here, which is somehow linked to this aspect. So most of the cases you are when you consider a cloud distributed environment, this stateful application like Mongo or whatever are not single instance. No, they are like a small cluster for different reasons, like fail tolerance, scalability, you name it. What is the most important? Still, there is a central. And this is very, very valid basically for any distributed application. There is a central aspect that you need to take into consideration when you define the way these instances across a cluster synchronize their data, which is which goes under the name of CAP theorem. I'm not sure you heard about it, but it's kind of the foundation of any distributed system. And basically, the CAP theorem says that a distributed system might have only 2 out of 3 properties respected when these properties are consistencies, availability, and partition tolerance. I wonder if you how you are in case you would have multiple instances of the same service, how your migration mechanism will deal with this type of constraint, and how you can ensure that somehow then what it comes up after the migration is kind of either you respect availability and consistency, either you respect partition tolerance. I didn't find a discussion around these aspects in the work.
Okay. Well, in general, it would go towards consistency. And there's also a question that's very similar to the one that Geo did about how can actually I synchronize distributed processes that are actually working together. In theory, like with the MTCP, that would be possible, but of course there will be a period where this is basically not reached. Are you hearing me? Oh, okay. So it would be able to handle whatever connections that actually are established to that application, and it could be able to recover those connections, assuming that they would have like a type of a connection which would wait for the application to be back again. In general, in terms of consistency, we would make sure that all the requests that are being received and also all the messages that have been sent would be bufferized in the level of the protocol to make sure that they are going to be delivered. Yeah, that's pretty much it.
Yeah, I also, there is another part, which is, I mean, I would like to ask you some more questions. And somehow, I think what is, and this again relates a bit on identifying the best context where this can make sense, no? The truth is that in modern microservice architectures, no, you in terms of what is in memory, you don't really care, no, because usually you are dealing with the RESTful APIs, even though they have a state behind. When if something goes wrong with the request during the migration, you have when the new instance is up, everything works again to the next request and so on. So can you identify a specific set of use cases where, for example, the in-memory part is crucial in the containerization world, and taking into account also somehow that you cut out, of course, all these pure stateless interaction from the pipe because they are not indeed relevant.
All right. I think go towards in the big choice of applications that we actually decided to evaluate. We actually went to we did some research in order to see like what are the most common applications that would be running into like a microservice like a deployment, and we end up with some queue applications, meaning that some of those applications, they actually do not persist all the message. In most of the cases, they are just into memory. So for example, like in the case of failure, you actually can lose this data. So it's just a matter like of trade-off, like you can actually enable them to be persisting the data, but in some cases you don't have this option because you have way too much data. So that's why we decided to actually evaluate it like the MQTT, RabbitMQ, and all like Mosquito and those types of applications, because they usually consist on having those messages into memory for the sake of being able to deliver them as fast as possible. So that would be one of these examples, and those types of applications are applied to a very huge range of other applications that consuming that data and actually make some like processing, some decision after that data.
Mm-hmm. So then this trigger another question that I had in mind. So basically, this means that in this context, this type of application regardless the migration aspect, have an issue in terms of state management, right? Because of course, as you mentioned, it's typical in this queue management system that you don't persist everything, or you don't persist everything immediately for a matter of speed. So if something goes wrong before the state is persisted, that messages in the queue are lost. This basically points to the fact that, and I'm not sure how much you thought about this, but these mechanisms that you have in place can actually be efficient for, efficient, adopted also for the case of, let's say, healing, self-healing of the system and restoring it without the need of any kind of migration at the same exact point also for the memory aspect, so implying that you are not losing these messages that were just only in the memory and not persisted. Have you thought about that? And I don't know if you made an experiment or just thought about that.
Well, in general, like the experiments in general made sure that all the messages are actually delivered. I didn't exactly went to this direction, meaning that the overall idea was actually, I mean, this can be also applied. For example, there is nothing saying that you couldn't create a checkpoint for the sake of like not losing the data. Actually, this is one of the tasks of the execution agent, because it does create the checkpoint, and once that the checkpoint is created, it makes sure that the data is being delivered to the new location and the application is restored as previously. In general, like this checkpoint could be used as well to recover or even to replicate the process as needed. As I said before, like it's all for the sake of consistency. It does come with a trade-off of like downtime, but it's actually tries to make sure that all the data is actually delivered. I'm not sure if I replied to your answer.
It's fine. It's fine. So I think I don't have anything else to ask Paulo. And again, congratulations for your great work, and thank you for your presentation and insights.
Thank you. Thank you for joining.
So thank you, Federico. I think we will now leave the floor to the advisors. So we will start with Daniele. If you can hear us.
Daniele?
Yes, thank you very much, Paulo, for your presentation, which I really enjoyed. I think what Paulo tackled during his PhD is a very relevant topic, not just for the scientific community, but for the industry as a whole, also as highlighted by Federico. And I am actually convinced that the solution that he devised can find application not just in the fog computing, which is, well, the focus of his thesis, because this comes as a part of a large-scale European industrial doctorate project on fog computing, but also in the wider setting of the edge to cloud continuum. So I'm actually quite positive about the fact that Paulo's work can have a lasting impact on both the scientific and the technology community. Thank you.
Thank you.
Thank you, Daniele. So now we let you speak.
Okay, so I'll try to speak with a loud voice so that the remote people can hear me. First, let me thank all the members of the committee, those present here physically, some of whom woke up crazily early this morning, and also those who could not attend in person. Thanks a lot for being here. While listening to your presentation, Paulo, I was thinking again about the whole journey. The journey started actually. We proposed a European project, we got it accepted, and we started recruiting. And there was this problem finding the last PhD student, right? So we were supposed to recruit 8, and we had 7. At some point, time was running, and we were under threat of wasting. And actually, a little miracle happened because I was in contact with your master thesis supervisor, to whom I've said, I mean, look, I mean, I'm desperate. I mean, and actually, he pointed me to you, and this is how we got in touch with each other. And things worked well, and we interviewed you, and you came here, and so on. I wanted to highlight the fact that you've worked as part of the FOGRU European Doctorate Program. This is something that provides great opportunity and puts a lot of pressure on the students, both of them, opportunities and the pressure. And I want to emphasize the fact that not everything that Paulo has done during those 3 years appear in the document. Paulo has had obligations of mobility. So he has moved from Brazil, but he has spent extensive periods in Italy at UHupper with Daniele, also in Spain, in Valencia, to run actual experiments and to actually deploy for platforms. This turned out to be an extremely interesting experience, considering that this was right in the middle of the COVID lockdown.
Yeah.
So we had a very interesting time. The other thing is that this doctorate program had a strong emphasis on innovation and entrepreneurship through trainings provided by EIT Digital, through a number of events. And actually, I hope that what we could see today, that actually your work has a real-world impact, maybe also comes from that aspect of your training. So, of course, the greatest impact is about saving Pokemon users.
Naturally.
Right? And this is obviously the most important impact of
The
the
only
work.
important point is our life.
Exactly. In yours, maybe, again. I wanted to emphasize the fact that maybe, well, I did not realize the Pokemon aspect until today. But at least what I've seen is the work has had scientific impacts. And we can see this through publications, through this very nice thesis you have written, and also on industry. And one thing I would like to mention is that this work has attracted the attention of industry. And this is not just the usual discussions like, yes, we should see each other sometime and have lunch and discuss one day, where you're actually currently working on improving the software to bring it from the state of a prototype, and we all know what prototypes look like, to bring it to the state that it can actually be used by other people. So this is, I think this is an extremely positive outcome of this thesis, that actually this work has had and has attracted the attention of industry. I just want to finish saying that supervising your thesis has been a real pleasure. It's been great. We've had lots of discussions on lots of different topics. And of course, I wish you the best for first finishing the transfer work and for whatever else you will decide to do with your life. So thanks a lot.
Right. Thank you.
So thank you, Guillaume. I'm the last one, but I still have questions.
Okay.
Sorry for you. So I have the first question about your second contribution, and it's about the limits of your work around the experimental validation. Did you try to push to reach the limit where you cannot migrate anymore? So meaning, for instance, on the load injector, did you try to push the application up to the point where you cannot migrate?
So in the second contribution, there are two main limitations. Okay, The first one, it's basically the amount of layers that you can create. We actually realized that if you create more than 2 layers, there is no gain whatsoever. So from that point, there is no need to extend the validation. It does allow you to create 128 layers, as the file system allow you to do that, but there is no reason to do that. On the other hand, there is the part of the application. I actually turned it a little bit and gave it a little bit more of load in order to perform the migration. And it worked. Of course, it did increase the downtime, especially because the amount of data that are being persisted increases a lot. So basically the downtime is defined by the time of transferring the checkpoints. You can see that it depends on the moment that you start the migration, but as much as the application run, you're going to have more data loaded, like stashed into your disk. So it's going to take longer for you to move that data. So there was actually no big reason for us to evaluate like in a very big scenario, meaning that you're going to see the exactly same behavior as we expect. That's going to take longer to move the data.
Okay, and I have a question that was already asked in other aspects. It's about the comparison with virtual machine migration. So what we call in virtual machine migration live is when you have a really short interruption downtime, which is less than 1 second or a few seconds. So you were putting in the slides that you consider your solution as live, but you still have 10 to 50 seconds interruption. So what do you call live?
Yes, that would be basically meaning that you can perform and start migration even before stopping the application. That's what I consider to be live in this case. You can actually, once again, this is going to depend on the transference and the whole thing. I do not do like incremental type of migration, like that's actually quite common for virtual machines, but rather something actually that you can perform on the files that you usually to constitute your container. Usually this is like the biggest part inside a container because it's supposed to be lightweight. And after that would be the memory size, basically the space that you have allocated that you need to be that you need to grab it from memory to migrate. So yeah, that would be how I define it.
We have a last question that you couldn't guess or have. So you're easing the mobility of IoT device users. So Pokemon users, for instance. And in the end, it will be more devices, more users. And what about the environmental impacts?
In what sense?
So you're easing the number of devices, of mobility, and so on.
Mm-hmm.
And this has already a lot of environmental impacts. So did you consider this in your thesis or not at all?
No, not really. No, I didn't go to that direction. That's actually a little bit out of our scope. We thought about most of it about how can we actually fix the problem, and we didn't talk about specifically the consequences, but rather to try to deliver something which does not create like a big overhead to the environment.
Thank you. So jury members will meet in a different room.
All right. Okay, thank you. Thank you, everyone.
Okay, so Daniele and Federico, you can disconnect from this Zoom session and connect into the second one. I will be there in a couple of minutes.
On enlève le sac. Il y aura des gens. You will stay in.
Where?
Yeah.
Thank you very much. Done it? Yeah, finally. To wait for the final paper, and we're going to have a full text saying didactic and hopefully, don't say that if you just get didactic, it's a very good presentation. I don't know. It's done. Yeah. How do you feel? Everything hurts. Like I'm so nervous that everything is stiff and so. It's but I think it was very chill. In terms of questions. Yeah. Just the last one. Pushing. Yeah. No. Yeah.
No, I didn't mean anti-seed, sorry. That's one of the other part of the
yeah.
not the, not the,
Yeah.
I would say.
Yeah. I actually like. But yeah, it's done.
You want a coffee to relax?
Yeah, actually, you have time. You get a coffee.
Yeah, you have at least 20 minutes.
Coffee.
Or if you prefer to stay here,
We
Yeah,
can
we
bring
can bring
you
one. Yeah.
j'ai dormi dans une position qui fait mal le lendemain matin.
So yeah, the reception was really well. Are you okay? Yes. So everything's well? How do you feel?
Oh, everything hurts.
Yeah, you will bow. I mean, probably. Sorry. Okay, so now we are gonna do everything, right? Okay, you can go. I was just going to finish something. So the normal business is. No, thank you. No, thank you. You know what you could do maybe? Because she didn't drink.
Yes.
But you have it. Okay, so everything is good. And you have cups as well?
Yes.
Okay, good. Then everything is fine. Okay, cool. And we need to bring her. I sent her a message. I'll tell you that later. Bring her a pop or something.
your PhD thesis work on migrating application in fog computing environments. So the subject is important and timely for cloud system. And your thesis was conducted in the context of the Fog European project in collaboration with your company, which was really appreciated from the jury. So your presentation was clear and pedagogical and well illustrating your scientific results. You provided a clear and solid answers to the numerous questions that we had, showing that you have a good understanding both on the technical aspects of your contribution and on the broader view on your domain, so the fog computing. So your thesis also opens interesting perspectives on container management in the edge to cloud continuum, so both for academic and industrial sites. And for all these reasons, we are really happy to anonymously deliver to you the diploma of Docteur en Informatique de l'Université de Rennes 1. So congratulations.
Thank you.
Thank you.
Well, I just have to thank you, all of you. Thank you very much for joining, for being here today. That's actually very, very important to me. Thank you to every friend of mine which is here as well. Thank everyone that's joining online. They were like a very important part of this whole journey. Like, thank you for everyone that are in Spain, that are in Italy, and that actually supported me in this whole process. And yeah, I think I have to especially thank you to my family, to my whole family in Brazil. Like, they have been so supportive during this whole thing, and especially my parents. And yeah, that's it. Thank you.
So we're going to close the video conference and the YouTube stream.
Yes, yes.